Electrons in your body are breaking the classical rules of physics right now. And that rule breaking is the only reason you exist as solid matter instead of a collapsing smear of charge. If we tried to build atoms using only classical physics, they would instantly self-destruct. An electron is negatively charged. Opposites attract, so the electron should spiral inward like a satellite losing orbit, radiate away its energy, and crash into the nucleus in a tiny fraction of a second. No stable atoms, no chemistry, no you. Quantum mechanics solves this by imposing a radical rule. Electrons are only allowed to exist in specific quantized energy levels, like discrete rungs on a ladder. They can never occupy the forbidden spaces in between. These allowed states are what we call orbitals, three-dimensional standing waves of probability around the nucleus, defined by Schrödinger's equation. Think of a guitar string. You can pluck it in many messy ways, but it only sustains certain notes, standing waves where the vibration fits perfectly along the string's length. Orbitals are the allowed notes of the electron wave, not as a little planet circling a sun, but as a smeared-out cloud. Each orbital has a well-defined energy. An electron in one of these states does not radiate energy continuously, it just sits there, stable, as long as it stays on that quantum note. That is why atoms don't collapse. The smallest atom, hydrogen, has one electron sitting in the lowest energy orbital. Helium has two, forced by the Pauli exclusion principle to have opposite spins, a purely quantum property that prevents identical electrons from piling into the same exact state. This exclusion, more than anything else, gives matter its structure. As we add more electrons, they fill orbitals in a strict sequence, shells and subshells. The pattern this creates is the periodic table. Why does sodium explode in water while neon just sits there, inert? Quantum mechanics. Sodium has one loosely held electron in its outer shell. It wants to give it away to reach a more stable configuration. Neon's outer shell is already full, with all its orbitals neatly paired, so it's chemically content. Chemical bonds are just atoms sharing or swapping electrons to reach lower total energy, constrained by quantized orbitals and the exclusion principle. Covalent bonds form when atoms share pairs of electrons in overlapping orbitals. Metallic bonds arise when many atoms contribute electrons to a collective sea that can move freely, giving metals their conductivity and shine. The hardness of diamond and the slipperiness of graphite both come from how carbon's electrons arrange into very different bonding networks. Every time a bond forms or breaks, electrons jump between energy levels, but they can't glide smoothly. The jumps are quantized. When an electron drops from a higher orbital to a lower one, it must release a precise packet of energy as a photon, a particle of light. The energy difference between the two levels determines the photon's color, or more precisely, its frequency. A big energy gap means a high-frequency bluer photon. A smaller gap gives a redder one. This is why heated objects glow red, then orange, then white as temperature rises. Countless electrons in atoms and ions are being excited by thermal collisions and then falling back, emitting a whole spectrum of photons. The detailed spacings of those quantum levels give each element a unique barcode of spectral lines. If you pass starlight through a spectrograph, essentially a precise prism and a camera, you see exactly those barcodes written in the sky. Dark absorption lines, where atoms in a star's atmosphere have grabbed specific photon energies. Bright emission lines in nebulae, where excited atoms are radiating them. From Earth, we can read the temperature, composition, motion, even magnetic fields of distant stars, all because quantum rules dictate which photons their electrons are allowed to swallow or spit out. The same rules explain why solids are rigid, why some materials are transparent while others are opaque, and why the sun shines by fusing hydrogen into helium, rearranging nuclear and electronic energy levels, and flooding space with light. The everyday world, from the color of your eyes to the solidity of your chair and the light from the nearest star, is quantum mechanics made large and slow. But the story becomes even stranger when we stop thinking of particles as merely having allowed energies and start asking how their very identity and individuality can blur and entangle.